Welcome. Earlier, we saw that relative extrema are critical values, but not every critical value is a relative extremum. In any case, we need to know if the critical value is a relative maximum or relative minimum more specifically, rather than just that it's a relative extremum. We can use the first and sometimes second derivative to make this determination. We will see now how we can use the first derivative to do this. It goes by the rather prosaic name of the first derivative test. So we have a function f which is differentiable at most numbers, and c is a critical value. If f prime is negative, if x is close to c and less than c, and f prime of x is positive if x is close to c and bigger than c, then c is a relative minimum. In other words, when you look at the sign chart for f prime, when you cross c as you go from left to right, if f prime goes from negative to positive, then it's a relative minimum. If f prime is negative, then f is decreasing, and if f prime is positive, f is increasing. So our assumption says that as we go left to right, f goes down as we approach c from the left, and then goes up as we leave c and proceed further to the right. In other words, first go down to c, then we go up from c, so c is a relative minimum. If the situation is reversed, then I have a relative maximum. That is to say, if as we cross c when we go from left to right, f prime goes from positive to negative, so f goes up to c and then goes down, then c is a relative maximum. If f prime does not change sign, so f is increasing on both sides or decreasing on both sides, then f does not have a relative extremum. So the way we use this test is that we do the sign chart for f prime, then look at the sign changes in f prime at critical values, and use this test to determine if for each critical value if it's a relative maximum or relative minimum or neither. Let's look at examples of this test. First, we will do a couple of examples where we've already done the hard work, which is doing the sign chart for f prime. Our first example is x power 4 thirds minus 8x to the power 1 third. We did the sign chart earlier. It's on slide 54. Here is the sign chart. We go left to right, and for each of the two critical values, 0 and 2, we look at the sign chart and sign changes. As I cross 0, f prime does not change sign, so 0 is not a relative extremum. As we cross 2, f prime goes from negative to positive, from left to right. So it decreases to 2, increases as we leave 2, so 2 is a relative minimum. So that's our determination using the first derivative test. Let's look at another example. This is x minus 2 power 4 times x minus 4 power 2. We did this in slide 55. This is the sign chart. So there are three critical values this time, 2, 10 thirds, and 4. So we'll go left to right, look at the sign changes at each critical value. As I cross 2, f prime goes from negative to positive. So f is decreasing to 2, increasing from 2 to the right. So 2 is a relative minimum. As we cross 10 thirds, f prime goes from positive to negative. So up to 10 thirds, down from 10 thirds. So 10 thirds is a relative maximum. As we cross 4, f prime goes from negative to positive. So 4 is also a relative minimum. Okay. Now we are going to do an example where we are going to do the whole 9 yards. So we start with a function. We will find its derivative, find its critical values, do the sign chart, and then determine the relative extremum. The function is 3x power 8 thirds minus 48x power 2 thirds. Finding the derivative is easy because all I have to do is the power rule. Derivative of 3x power 8 thirds is 3 times 8 thirds, x to the power 8 thirds minus 1. 3 times 8 thirds is 8, 8 thirds minus 1 is 5 thirds. For the second term, I have minus 48 times 2 thirds x to the power 2 thirds minus 1. 48 times 2 thirds is 32, and 2 thirds minus 1 is negative 1. Now I have to simplify it, so I'm going to write the second term as a fraction, 32 over x power 1. Put the two terms over a common denominator, which will be x to the 1/3. In the first term, the denominator was 1. I want to make it x to the 1/3, so I need to multiply the numerator by x to the 1. In the second fraction, I already have the common denominator as a denominator, so I don't need to change it. X to the 5/3 times x to the 1/3 is x squared. Combine the two fractions into 1 and factor the numerator. I can factor out an 8 and then have x squared minus 4 as the other factor, which factors as x plus 2 times x minus 2. H prime is 0 at negative 2 and 2. H prime is not defined when x is 0, and since the original function is continuous at 0, that's also a critical value. If you arrange the critical values in increasing order, they go negative 2, 0, 2. Left to right, my intervals will be negative infinity to negative 2, negative 2 to 0, 0 to 2, and 2 to infinity. As usual, I will do the sign chart by doing test values. I picked 8 and negative 8 so I can do the cube roots. There is a cube root in the denominator. At negative 8, the numerator is positive times negative times negative. The denominator is negative, so the whole thing is negative. Can go through and do this for each of the other intervals. I will leave it to verify that the signs alternate, which means that as we cross each critical value, the sign of h prime changes. So each critical value is a relative extremum. When we cross negative 2, h prime goes from negative to positive, so it's a relative minimum. As we cross 0, h prime goes from positive to negative, so 0 is a relative maximum. And finally, when we cross 2, h prime goes from negative to positive, so 2 is a relative minimum. One thing you will notice is that if there are no vertical asymptotes, then relative maxima and relative minima alternate. This will always be the case. If a function is differentiable or at least continuous throughout an interval, then within that interval, relative minima and relative maxima must alternate. But if you have discontinuities, so for elementary functions it means if you have vertical asymptotes, that may not be true. So you can have a relative minimum immediately to the left of a vertical asymptote and also immediately to the right of the vertical asymptote with no relative maximum in between. This concludes our calculational examples, and I will stop this here.